Okay, so I think we've hit the hour. So yeah, well, welcome everyone, and we have a guest speaker today, as you know. I'm really pleased to introduce Rachel Kurchin, who's at CMU. Rachel did her undergrad degree in physics at Yale, and then was at MIT for a good amount of time, doing a PhD in material science and engineering, working in the photovoltaics lab, I think with Tonio Bonacisi and people there, and has since then been at CMU as a kind of molecular sciences software institute postdoctoral fellow, and maybe other postdoctoral positions at CMU, working on computational methods for material simulation, molecular simulation, and for battery and catalyst applications. But I think the way that sort of I got to know Rachel's work is through the software and Julia side of the effort, and that has a lot of interesting connections and parallels to things we're trying to do in CESMIX. So we're really pleased to learn about what you've been up to and Chemellia and everything you've been doing. So yeah, please take it away.
Thanks so much for the invite and the intro. I'm very excited to be virtually back at MIT for the day. I wore an appropriate shirt for the occasion. And yeah, I'm excited to be here talking about some work on building a materials computation ecosystem in Julia and some lessons learned along the way. So one lesson I learned in grad school is that usually chronological order is not the best order to tell a story in, but I'm actually sort of violating that maxim today, and this story will be mostly chronological because I think that actually kind of illuminates some things, and given that it seemed like there was some curiosity about sort of the process and the motivation behind developing some of these packages, a lot of this will actually be sort of chronologically organized. And I should say, feel free to interrupt me at any point if there are questions or discussion points, and I'm happy to answer things along the way and or at the end. And if there's some time, I have a little bit of a live demo of a few of the things that I'll talk about that I can switch over to and show off a couple of things. Yeah, so to give a little bit of context, I started my postdoctoral work with no Julia experience in September of 2019. In December, our group was awarded this ARPA-E collaboration grant. We called ourselves ACE, the Accelerated Computational Electrochemical Systems Discovery Team. And it's a fantastic collaboration with folks from a bunch of different, both companies and academic settings. And this was kind of the kickoff point, given that we were collaborating with Julia Computing. I'd been starting to dabble with Julia a little bit, and this was really what sort of pushed me into really jumping all the way in and learning. And I'll give just one more slide of context about this project, because I think it's an exciting project. And if you want to learn more, we do have a website. It's just cmu.edu/aced. I probably should have put this at the bottom of the slide. We also have an archived manuscript sort of outlining some of this vision. I can send these slides to Yusuf afterwards. There are a few other links in here that might be useful for folks. So this is kind of the big picture vision of this project. I've often referred to it as, we're not really reinventing the wheel in most places so much as kind of building a superhighway. We're trying to automate the process of designing materials for these various electrochemical applications in as much of a sort of humans out of the loop way as possible. And so we have sort of several scales of simulation, both the sort of atomic scale and then the kind of device level where we're thinking about kinetics and transport. And in both of those contexts, we're interested in developing machine learned surrogate models that can drop in to sort of accelerate things and reduce the computational load. And so where my work specifically slotted in and what kind of got all of this started, oh, sorry, I should have said, yeah, so we have two kind of phases or case studies where we're trying to apply this workflow. In phase one, we were looking at discovering catalysts for electrochemical ammonia synthesis. And in the second phase, which is what we're mostly focused on now, developing new liquid electrolytes that can block dendrite formation in lithium metal batteries. But we're really hoping that the general type of, well, of course, there's tooling that's specific to those applications, that this workflow can be a fairly generalizable kind of paradigm. And so where I kind of slot in is mostly at the level of the surrogates for the atomic scale simulation. And in particular, I got really interested in graph-based models and sort of set myself as a first really way to kind of jump into Julia and learning how to, develop packages and write nice code to sort of re-implement something that already existed in Python with a few changes and I like to think improvements in Julia as kind of a starting point. And because I'll be talking about that and about graph-based things for the rest of the talk, I thought I'd give sort of a brief aside with some background about graphs and the particular matrices and graph related objects that I'll be referring to, just so that everyone's on the same page. So this may be review for some folks, but maybe some folks don't know all of this terminology. So I'll go through this here. So a graph is an object with nodes and edges. You can think of like ball and stick models from a chemistry class, which is in fact very similar to what I'll be thinking about. I'm mostly thinking about graphs where the nodes are atoms and the edges are, you could think of bonds, or perhaps more generally just kind of neighbor relationships between atoms. Obviously, in an organic context, bonds are fairly well defined, but rather notoriously in sort of inorganic or crystalline solids, what exactly is a bond is almost more of a philosophical question than a scientific one. So I tend to think of them more as sort of neighbor relationships between atoms. And we can represent these graphs via matrices. So if we give each node a number, we can make what's called the adjacency matrix, which in an unweighted graph simply has a 1 between two, unweighted and undirected, I should say, where we will go to weighted graphs, but not so much thinking about directed graphs. For this context, we have a 1 where if a node is connected to another node, so here we have 1 is connected to 2 and 3, and this is symmetric across the diagonal because it's undirected, and similarly, so this adjacency matrix represents the structure of this graph. I'll note this also possesses a nice property that folks refer to as equivariance, meaning that if we switched 2 of these nodes, the adjacency matrix would switch accordingly so that the model action won't really care about what number we happen to give which node, which is a nice property because that's just kind of an arbitrary piece of information that we're injecting. Which node has which number doesn't really have any particular meaning in the context of these chemical compounds. There's no inherent ordering between different atoms in a molecule or in a crystal. We can also have self loops, in which case we would add entries in this adjacency matrix. So if one were connected to itself, and this becomes important in things like periodic structures. And I'll show for these little cartoons here, again, just unweighted graphs. So adjacency matrices are binary, but in the actual applications I'll be talking about, I'm actually working with weighted graphs. So you can imagine these numbers being different according to the weights of the edges, which you can think of if atoms are closer together, they might have a larger weight. Farther apart, there might be a smaller weight between those edges. So this is referred to as the adjacency matrix. And another important matrix we can construct is called the degree matrix. This is always a diagonal matrix, and it just says how many ends of edges are connected to any given node. So in this case, note that the self loop counts as 2. So the degree matrix for this graph would look like this. And from these 2 ingredients, we can construct what's called the Laplacian matrix, which is just the difference of the 2, and it looks like this. And when I first learned about this, you kind of look at it, it seems like a rather arbitrary thing. Where does this come from? What does it mean? But the name is quite evocative. So if you think about a Laplacian operator in a differential equation, we know that that refers to sort of diffusional types of processes. And in fact, the action of the Laplacian, which is often referred to as graph convolution, is in fact a diffusional action. So we can demonstrate this very simply. If we think about a very simple graph signal, so we're just going to start with a 1 on node 5 and zeros everywhere else. That's going to be our initial signal, our V1. If we hit this with the Laplacian, so we multiply by it, you see that this signal starts to sort of diffuse or propagate along the edges of the graph. So after one step, we have this. And if we repeat this process again, we can see that it now has diffused again, sort of along these 2 edges here, over across the graph. So this action is very nice. It sort of respects the structure of the graph. This is a nice way to let information flow around in a neural network. I'll note as a side note that in these neural networks, usually we use what's called the normalized Laplacian. You'll notice that the sort of size of this signal is varying pretty drastically, and there's a way we can sort of normalize that. But again, to keep the sort of cartoons on the screen simple, I went with the non-normalized. So this is kind of the main ingredient in a graph, what's called a graph convolutional neural net. The one other change is that rather than a feature vector where we have a single number at every node, we can now assign a matrix to every node and just stack, or excuse me, a vector to every node and stack those vectors together into a matrix. So that feature vector becomes a feature matrix. And then our typical architecture would look something like this, where we have a graph convolutional layer, or maybe a few graph convolutional layers. Then the output of those needs to be pooled to get to some consistent length feature vector, because these graph convolutional layers can act on graphs of any size, but one of the dimensions of that output matrix will be a function of that size. And so if we have these densely connected layers at the end, they're going to have some fixed width. And so we need to have this pooling procedure in here as well. So again, as I mentioned, I sort of assigned myself a first project in Julia, which was kind of a re-implementation of what's called crystal graph convolutional neural nets. So there was a Python package called cgcnn.py that was the first implementation of these. And I sort of rebuilt it in AtomicGraphNets.jl with a few changes that I'll get to in a moment. But first I'll show, that even just sort of straight out the gate, before I really knew anything about, optimizing Julia or writing the code, especially nice or fast, we got comparable accuracy on this particular test case, which was predicting formation energies of all the stable ordered materials in the materials project database with close to an order of magnitude faster training time. So that was kind of gratifying and cool to see. And the other interesting thing was that for a sort of similarly set up model, we actually have about a quarter as many trainable parameters. So that's also interesting that we can get, it seems like comparable expressivity, at least on this particular test case, with substantially fewer parameters. So it's interesting to think about, what's going on there. And what specifically is going on has to do with the actual nature of the convolution operation. So in cgcnn.py, they're not actually doing what I described with building the Laplacian matrix and sort of multiplying that. There's a little bit more involved operation where they have these feature vectors for the edges as well, which are just these sort of Gaussian expansions of the distances between the edges. And so these have this whole concatenation operation that are hit with a separate weight matrix. And so given that this weight matrix is hitting this much longer vector because we've concatenated all of these edge features, this leads to a lot more parameters in a single convolutional layer. Because I should say these networks, the comparison cases were the same hyperparameters in terms of the number of convolutional layers and the width of the dense layers and all of this. And it actually gets even more complicated because this was sort of the initial version. And then they said, oh no, we need to actually do this other thing. And where we do this, well, I won't go into all the details, but basically there's an additional concatenation step and this sort of element-wise multiplication that they found that they needed to get this expressivity. As compared to a conceptually much simpler, I think, operation in AtomicGraphNets where we directly make use of the graph Laplacian. And so a single layer operation looks like this. And specifically, the other difference is that we are using weighted graphs, as I mentioned. So the edges have weights as opposed to just binary, is this atom a neighbor of this other atom or not? And my suspicion is that that is part of what gets us this sort of extra expressivity, is that we're sort of incorporating the weights in the graph. And so we don't need these sort of expanded edge feature vectors. Again, at least not for the specific test case that I'm showing here. It's possible that you might need that for other types of tests. Now, when I see these kinds of equations in any of these machine learning papers, I always need to sort of go through and figure out what's actually going on. What are the dimensions of all of these matrices that I'm multiplying together? So I'll go ahead and do that for you all here. So notationally, we'll say, oh, sorry, go ahead, please.
Can I ask a question to
Absolutely.
clarify? So if I understand your notation correctly, H is a matrix, right?
Sorry, X?
Capital H. So this is a so
I think X, yeah. So,
capital H, yeah.
Oh, X, yes, X is a matrix, that's correct. Yep.
It's a matrix. The size of this matrix equal the number of nodes times the number of features for each node. Is that right?
That is exactly what I'm about to say. Yes, you're running ahead of me, but I'm glad that I set up to ask a nice leading question. Yes. So I mean, I can animate in what I was about to do, but you're exactly right. So if we have a given graph with n nodes, then and the number of features at step t. So if we imagine multiple layers together, there might be different widths of these layers. Then exactly as I'm sorry, I don't know how to pronounce your name, but as was just astutely pointed out, the x's will in fact be of this dimension. So one dimension is the number of nodes in the graph, and one is the number of features per node. But we notice that this all works out, and critically it works out such that none of the trainable parameters depend on n. This one might look like it does, but I will sort of prove to you in a moment that it in fact does not. So again, X is just this is just sort of the notation that's used to say that we're just stacking those vectors all together. And so this is a single vector that gets stacked together n times, different one for each n. In contrast to the case of the bias matrix, where in fact the bias is actually only trainable per feature. So we're stacking n copies of the same vector here. And so you can see with that additional clarification that the W's and the little b's don't depend on n. So we can sort of convince us that this will work for a graph of any size that we put in. And then we have some appropriate pooling operation afterwards. Does that clarify the question? And I can pause here as well if there are any other questions.
Yes. Just another related question is, I wonder whether you consider edge feature as well. I think here you have only no feature. In many GNN, they also include, edge feature.
Yeah. So in this convolution operation, we do not accommodate edge features. And sort of what I was showing is that, again, at least for this particular test case, I can't speak to sort of a universality necessarily to this. We found that there was enough expressivity by using the graph, the Laplacian corresponding to the weighted version of the graph, to get enough there that we didn't need. So what the edge features typically look like, at least in the cgcnn.py, is it's in fact just this sort of Gaussian basis expansion of the distance between the nodes. So really the only piece of information that's there is kind of the length of the bond, if you will. There are very sensible kind of, physics, material science oriented reasons to think that that's a useful thing to do, to think of, if you imagine surrogатizing electronic interactions that take place at different distances between atoms, you're sort of capturing perhaps in some way different orbitals. So it's very envisionable that those things could be important. And I believe there's actually still an open issue in this repo to support convolution operations that can accommodate edge features. But this was sort of, as I mentioned, this was kind of the starting point of I was just learning how to develop in Julia, and I wanted to get to sort of a minimal working thing. And I thought it was really interesting that even with this much simpler convolution operation, again, we get these results for this test system that work just as well without needing all of those edge features, and you get away with many fewer parameters, which I think is kind of interesting. And again, I'm not making any claims that this will always suffice. I think in many cases you probably do need the edge features. Is that clear?
Thank you very much. Yeah, it's clear.
Great. Yeah, Victor.
Hi, Rachel. Thanks for clarifying this. I just want one more. It's still in this topic of
Sure.
weighted edges. So in this case, at least on this first iteration, is your Laplacian basically just for an undirected, unweighted graph?
It is for an undirected weighted graph.
Okay, but then I think maybe I missed it. What are the weights that you attribute to each one of the edges?
Yeah, so I brushed that under the rug a little bit. It's a very fair question. And there are a bunch of ways that you can do that. And it's kind of interesting. So the first thing that I tried was, and this is in fact still the default setting, you can just say, okay, I'm going to compute the distances between every pair of atoms, and I'm going to set the edge as the edge weight as some presumably decaying function of that distance. So it should, intuitively, I would think the weight should be larger if the atoms are closer together and smaller as if they're farther apart. Maybe an inverse square type of function would be a reasonable thing to do. One could imagine an exponential decay. And so the way that it's set up right now is that those are two functions that are built in that you can choose for this decay, or you can also supply your own function if you want the edges to be constructed as some other function of the distances. There's also support for another option, which is based on the Voronoi tessellation of the crystal. So if you break up the crystal into these kind of Voronoi cells, so every atom is surrounded by the volume in which every point in that volume is closer to that atom than to any neighboring atom. And this will in general give you some sort of polyhedron. And you can instead, this has the advantage that it also gives you a consistent way to determine what the neighbor lists actually are. If you do just based on the edge weights, then you ultimately need to set some cutoff, either in terms of the number of neighbors that you'll allow or the largest distance that counts as a neighbor. This Voronoi approach is appealing because it actually naturally gives you the neighbor list. The neighbor list is just any atom that shares a face of the Voronoi polyhedron with that atom. And then your weights become functions of those faces. So for example, the area of the face or the solid angle of the face, or perhaps you can do all kinds of things once you have this polyhedron constructed. So that's another thing that's also supported. And I was really excited about this. It seemed much more sort of, geometrically and intuitively appealing. Interestingly, again, on this particular test case of the materials project, it seems to underperform the cutoff-based version, which I was a little bit surprised by. But the option is there, and it may well be that works well for other problems. I have not done I've tested on a few different cases beyond this materials project data set, but I would certainly not claim to have done a completely extensive test of this on every envisionable data set you might want to use. Does that answer the question?
Yeah, that's very nice. Just one quick follow-up on the Voronoi tessellation then. Do you normalize the weights based on the total area of the polygons from the Voronoi tessellation?
Yeah, so in all of these, again, you can turn this off if you want to, but by default, the weights are all normalized. I think the default normalization is just you use whatever function you're using to compute these weights, and then everything gets normalized to the largest one. So the largest weight is always guaranteed to be 1. Yeah, so that's kind of the default behavior. And again, you can sort of get in there and tweak it if you want to. If you want some more sort of global normalization, as one might imagine you could want, you can also supply your own function to do that.
Thank you. That clarifies things a lot. Thanks a lot.
Great. Yeah, thanks for the question. Yeah, any other questions at this point? This is kind of the most nitty-gritty equation-y slide that I have. So I think if you're not clear on every aspect of this, you don't need to be too worried, because it won't build too much from here. I'm going to sort of go into the more sort of software development, sort of ecosystem building aspect of things from here. But I'm happy to take any other questions at this point on any of the sort of graphs.
Just one more quick question.
Sure.
So the node feature VIT, how you compute it? Is that the formula on the top left of your slide? Is that how you compute it?
Oh, okay. Yeah. So this is great. So the top left is actually, I probably should have made that a little more obviously grayed out. That's actually from the previous, that's the version from the Python version. So okay, there's kind of 2 questions embedded in there. So we have some initial features, and they are stacked together to form these X vectors. And then after that, they are computed via this convolutional operation. So say, I don't know if you want, let's go 1 index because we're in Julia land here. So maybe VI1 is our input features, and VI2, so I indexes nodes, and the superscript indexes how many layers in we are. So VI2 will be computed as we would compute X2, and then if we wanted, we could decompose it into the VIs corresponding to each node. Now, there's another question in there about how do you compute the initial inputs, and that's exactly what my next couple of slides will be about.
Okay, got you. Yeah, so yeah, I will follow your next slide then. Yeah.
It's a very fair question. I'm very glad that this is sort of set up such that you're asking these wonderful leading questions for me to seamlessly transition from one thing to another. So thank you. I swear he's not a plant, everyone. So okay, chemistry featurization was born out of my frustration. So this is exactly the package that I developed to build these feature vectors, and it was born approximately out of my frustration with standard approaches, both the opacity and the kind of rigidity of them. And this is not really to pick on cgcnn.py in particular. They really broke a lot of ground in a lot of ways. It's also an MIT project out of my own DMSE department, course 3. But I was not necessarily happy with it when I dug in and learned how to use it. So it ships with this big JSON file called AtomInit, and that's full of basically these bit strings. So you have these big vectors of zeros and ones, and these correspond, basically the numbers here correspond to different atoms. And if you dig into the supplementary information of the original paper, you can find that what this is a standardized encoding of this set of atomic properties. And so what they're doing, so number of categories tells you kind of the length of that bit string. So for example, in the group number of the periodic table, we'd have a string, a one-hot vector, basically with zeros and a 1 in the slot that corresponds to whichever group number we're in. Similarly for period, etc. For these more continuous valued features, you're instead dividing up this range into 10 bins, and you put a 1 in the bin that corresponds to the value that the feature takes for this particular atom. So this is all fine. This makes sense. It's a nice, standard set of properties. But I looked at this and it seemed very, first off, you look at these bit strings, and if you don't happen to find this table as I didn't the first time I started playing with the code, it just seems very, very mysterious and opaque. And also, suppose that I wanted a different set of properties, maybe fewer, maybe more. Maybe for these continuous valued features, I want to divide into different numbers of bins, or I want to space the bins linearly or logarithmically, or all sorts of things. There's no flexibility to do that. You'd have to sort of write the code to generate this JSON file and rewrite it from scratch every time. So I set out to write something that would be a much more flexible way to do this. And that's kind of where this idea of chemistry featurization came from. So this was initially sort of a submodule within AtomicGraphNets. And then I realized, this might be a sort of more broadly useful thing. And so we sort of split it out into another package. And the core design principles behind it are, 1, transparency. So I would like to know what information I'm encoding and how am I encoding it. 2, flexibility. So this gets at what I was just saying, maybe I want to include this feature, but not that other one. Maybe I want to have more or fewer bins for different features. This is another big one to me that I think is very often overlooked in these systems, which is invertibility. I want to be able to undo my feature encoding to the extent that I can. Obviously these continuous one-hot encodings throw away some information, and the inversion should tell me, okay, with what resolution have you actually encoded this? How much information is your model really getting about the value of this feature? Versatility, I'd like to be able to use this ideally on a bunch of different atomic systems. I think if you look at this world of machine learning on atomic systems, there's kind of a bifurcation between the folks who think about inorganic systems and crystals and those who think about, organic systems, molecules, proteins, all of these kinds of things. And a lot of that is for good reason. There are different types of tasks, different types of features that are useful, different sorts of structural fingerprints, all these sorts of things. But I think it's kind of unfortunate when they're so bifurcated that you can't share things between them, even when it might be useful. So another goal that I have for chemistry featurization is that it can hopefully be something that is flexible enough to be able to be usable by both of those communities, and also to kind of share things. If you have some sort of feature or method of analyzing a structure that's useful for a machine learning model in one domain, that you might be able to at least try it pretty easily in another domain and maybe find that it works. And related to this, extensibility. It should be easy for me to make that happen. If I have some idea, I should be able to implement it within this framework and use that to encode features of my systems, ideally alongside other features that are maybe already provided. So the initial concept here was kind of a one-stop shop for atomic representations, feature specification, encoding and decoding, as well as providing sort of standardized output types for the machine learning models we build. And we made this figure, and I'll note that this does not actually exactly correspond to the way that things work today for a couple of reasons, but the general flow is still similar. And I'll talk more at the end about what things look like now. So this is, again, corresponding to this timeline. We're back in July of 2020 or so. So the idea here was that basically chemistry featurization would function as a configurable way to take in some sort of a structural file and output something kind of conforming to those design principles that could be directly fed into a machine learning model. So we conceptualize there's sort of different components of this. One is the actual structure representation of the atom itself, which might be a graph. It might be a set of 3D coordinates, other sorts of things. You have a featurization scheme, which is composed of individual feature descriptors, such as those that describe features of a given chemical element, but could also describe pairs of elements or even larger neighborhoods. Those encode those features and then are stored in this overall featurized atoms object. That thing is then the input to your model, and it's also designed in such a way that it's very easy to sort of serialize and store, and it carries with it all the information of how the features were encoded and how to decode them, so that you don't sort of lose that and go back to that world of kind of opacity. So maybe I'll pause here again for a moment in case there are any other questions. Again, with the caveat that this is, a lot of the terminology is still the same, but the actual way that chemistry featurization works now is a bit different. And I'll show that in a sort of live demo if there's some time at the end. But are there questions about this idea and the sort of design principles that I've laid out or anything like that?
Rachel, is chemistry featurization used to calculate the initial feature needed for the graph neural network?
Yes, exactly. Yep.
If you can describe the mathematical, the description of how you generate those features, that would be great. I know from the software
for the case of,
here.
Oh, sorry.
But
I'm
the
sorry.
mathematics behind that maybe will be very interesting for me. Yeah.
Yep. So for the case of this, we call these element features, which basically means features that are determined only by the identity of a chemical element. So it doesn't depend on the oxidation state of the atom or its position with respect to anything else. So we have a sort of type hierarchy. There are atom feature descriptors, which are any features that correspond to a single atom. And then within that, there's element feature descriptors and also species feature descriptors. And the latter is meant to be for cases where it might depend on something about the coordination environment or the oxidation state or other information that you would need. The nice thing about element feature descriptors is that their values are completely defined by a lookup table. So all of these features are examples of those where you can just, and this is in fact exactly what we do, and I'll show this in my demo at the end. You can just have a lookup table that determines these values. And then the only other piece that you need, and this is another thing that we sort of take care to separate conceptually in chemistry featurization, there's the value of the feature. So, the group number of hydrogen is 1, and it's, and its covalent radius is some number of picometers. That's the value of the feature itself. That's more like a human digestible number. That's not necessarily what we would feed into a machine learning model. What we feed into the model are these things that look more like these bit strings. So then once you have the value, there's also the process of encoding that value. And very often that's with this one-hot encoding process, but it needn't be that. It could be something else conceivably. Maybe you want to feed an actual, continuous valued float that you just scale by some number. So we have support for something like that as well, called direct encoding. So for the cases of these element features, that is the computation of the value of the feature is simply what is the element, look up the value in a table, and then you have the encoding process, which can be whatever you want. There's sort of a plug and play aspect to this, but a very common answer is that one-hot encoding. Now, for features that aren't so simple that you can define them as a lookup table, you might need other functionality to determine them. So things like, if you want to have something that has to do with the coordination of an atom, you need to know something about the geometry. You need a function that takes in that structure and computes the coordination, or maybe you're interested in something that has to do with the whole structure. So a Coulomb matrix is a very common type of footprint, or there are many, a whole plethora, a zoo of different things like this. And the strength of what chemistry featurization has become, that's actually somewhat different to this sort of all-encompassing model that I showed here. And I'm jumping ahead a little bit, but it's a great question, is that it's actually become more of an interface where you're able to plug in your own functions to compute those things. And as long as you define types that dispatch certain functions such that chemistry featurization kind of knows how to plug them into each other and connect them together, you can use this kind of umbrella machinery, but have your own functions for computing whatever features you're interested in on your system, which we recognize may be quite different depending on the type of system you're working with. So I'll show more, at least for the element feature case, I'll show this kind of interactively later, but hopefully that at least partially answers your question.
Yes, it's very, very good. Thank you very much. So as you know, there in machine learning potential, there are many other kind of descriptor or feature, namely from bispectrum or the atomic cluster expansion, which is a very general form of generating the feature or descriptor.
Yep.
So I wonder whether the chemistry featurization could be able to incorporate, those, feature as well.
I absolutely hope that it could. There is, first the ACE is actually, so I've actually had a couple of conversations with Chris Ortner, who's been involved in developing some of that stuff. And I think it's a really neat effort that they're doing over there. My hope is that the framework that we've set up is general enough to do that. There is not currently support for specifically ACE at the moment. It's basically two of us who are working on this package right now, and we're understandably biased towards building the stuff that we directly intend to use. But I am very, very open to pull requests and issues and suggestions. You can find all of this stuff. So we have a website, Chemellia.org, which is a bit spare at the moment, but we have a GitHub org, Chemellia, which is where most of the action happens. And so I'm very, very happy to take, suggestions or if you look at the code and there's something about the way the interface is set up that you don't think would support something else, that it's not actually as general as we hope it is, that would also be very useful to know. I think it's young enough that there would still be room to hopefully make those adaptations, because we really hope that it can be general enough to exactly as you say, sort of accommodate all of these different kinds of featurization schemes. Absolutely.
Thank you.
Thank you. These are wonderful questions. Thank you all so much for the active participation. So again, going back a little bit to the timeline, was very fortunate to have some more support for this project come out. So late 2020, I was awarded this MolSI fellowship that Yusuf mentioned in the intro, and this was really great because it gave me kind of the leeway to have this be like the main thing I was focused on for some amount of time, which was really wonderful. And they also provide great mentors that you get to meet with twice a month and give sort of, which was really, at that time I was still learning a lot about things like, how to properly set things up on GitHub and get CI running and code coverage and all of these things. And so it was really great to have mentors with a lot of experience in that could sort of point me in the right direction for troubleshooting those sorts of things. And then a couple months after that, my wonderful GSOC student Anant emailed me for the first time in January of 2021, and he went on to be a Google Summer of Code funded student for the summer of 2021. And he's been just absolutely instrumental in the continued development, especially of chemistry featurization, but really of the whole ecosystem. Has contributed just so many great ideas for the way things are structured and how to sort of properly kind of separate concerns and keep different functionalities from overlapping when they don't need to. And so I really can't speak highly enough of him. And he's now actually working at Julia Computing and I think he's really enjoying and has found a great landing place there. And is still, although not full time, unfortunately for me, but is still an active contributor to the project. And so he's been really wonderful. And it was actually shortly before the start of GSOC that summer that we actually kind of rebranded and created this Chemellia ecosystem, which I already mentioned. I actually, again, thanks to the MolSI folks, they paid to have a bunch of stickers, little decals printed with this beautiful logo, which was Cormelian, who many of you might know is kind of one of the Julia graphics guys, helped me to design this logo. The MolSI folks had a bunch of decals printed, and I actually mailed an envelope of them to Yusuf. So I guess you guys are mostly remote at the moment, but he's got a whole little packet of these stickers, and if folks want them for their laptops or their phones or whatever, they're very, very nice, very sort of high quality. I've got them on my coffee mug and all of this, so I sent some along for you guys if you want them. And yeah, so the idea of this this Chemellia ecosystem is exactly this, an ecosystem for machine learning with atoms that encompasses these packages that I've talked about, and as well as a few other things, some of which I'll touch on a bit later. And so the thought is that chemistry featurization is in some ways sort of an entry point to this, that you would use that to do the featurization and then create these objects that you can feed into these models that would also sort of be a part of this ecosystem. And so, as I mentioned already, we've got this website, which is mostly just GitHub links right now. And the GitHub organization is really where most of the action is happening. Most of the I'm pretty sure all of the packages that are actually released and registered, we do have reasonably complete docs pages for them. So you can go take a look and sort of teach yourself about it. And again, very open to issue filing if there's something in the docs that that is not clear or out of date or doesn't work, 100% open, always open to that stuff. I want this stuff to be up to date and informative and helpful for people. So then we come to Juliacon 2021, where I gave a talk on Chemellia that was, I think, well received. It's got several hundred views on YouTube, which I'll take. But also quite excitingly, Michael Herbst, who I know is part of the CESMIX group, and I, as well as a couple of other people, co-organized a Birds of a Feather session on building a chemistry and material science ecosystem in Julia. So these sessions are not recorded, so you can't watch it, but the link here, and I'll send these slides along, takes you to some notes that we compiled in a GitHub repository, so you can get a sense for what we talked about. And this also really spurred a community that is still kind of ongoing. So we sort of hijacked, in some sense, the JuliaMolSim organization, which Michael and Christoph and several other people had been using to host a variety of projects that they were working on. And this sort of became the community hub for this. So we have a Slack with various discussions going on about a lot of these different things. And so I strongly encourage anyone who's interested in joining these conversations to head over there. There's a link where you can just get yourself an invite to the Slack. And this Birds of a Feather session led to the development of AtomsBase.jl. This was one of the big things that came out of this discussion, that we need something, the sort of crux of it was we need something like ASE for Julia. So if you've done anything involving atomic simulation or any of these kinds of things in Python, you're probably familiar with the atomic simulation environment, which has sort of at its core these atoms objects, a unified or sort of a versatile representation of atomic structure. So storing things like coordinates, boundary conditions, unit cells, all of this. And then that can be fed into, they have an interface for feeding that into many, many different kinds of simulation tools, density functional theory, molecular dynamics, all sorts of things. And so the sort of core idea here was ASE for Julia. Given the way that Julia is set up, we decided to do this as primarily as actually an abstract interface. So we basically have a list of functions that your representation, so you can implement a representation of a structure, and as long as it dispatches a relatively small set of functions that we've specified, then all the rest of this interface will work. And so this has been released as of this past September, or I can't remember how I dated this, if that was when the initial commit, that was either the initial, that may have been the initial commit on the project. Maybe it's, at any rate, it's released and registered, you can use it. And I'll demo a little bit of this later as well. And the hope here is that this will really become a go-to option for, I know Michael is already using this in his DFTK package. I understand there's been some use of it for some other things within CESMIX, which is really exciting. And my hope is that it will become kind of a go-to thing for this, so that you could imagine, using the same structure representation or this interface anyway for going between different things. So maybe you want to build an AAMD setup where you need to interface between density functional theory and molecular dynamics. And as long as they both, and there's different types of actual data layout for those things that might be good for representing your structure. But as long as both of those dispatch this interface, it should be relatively seamless. I'm hoping someone who's really good at things like Mach-E or plots will make recipes for visualization at some point. I think there are a lot of really exciting directions that this could go. And so I'm very excited about this project, and I encourage folks to check it out and make suggestions, try to implement it in your own package if that makes sense. And this also was one of the things, I knew about interfaces, and obviously there's a wonderful graph interface for Julia that I'd already been making extensive use of. I think it was building AtomsBase and being involved in this that really, really kind of triggered my appreciation for how powerful this idea could be. And I've already alluded to the fact that chemistry featurization now actually takes in large part the form of an interface. And it was this effort that sort of inspired that and led me down that path. And another part of what pushed me in that direction was, as we were starting to try to implement different types of features and structure representations and all of this for different models that we were working on building, chemistry featurization was getting really bloated because we needed to support all of the different packages. We needed to have dependencies on all of the different packages that each of these different models was pulling from. And so, you might have something where, this is just to give you a sense of the kinds of frustrations we were having. At the beginning of a PR, nothing's going to pass. Maybe you're not done you know, supporting all the tests or updating them. And then, okay, all right, now I fixed it. It seems to run on Windows, but it's broken on the other ones. And then later you try to fix that and you have almost the exact complement of that, where now it's running on Ubuntu and Mac, but it's somehow failing on the Windows now. And it was just, we were just having this, you know, almost every time we tried to add or change something. And so this was a big part of what inspired me to sort of rethink this. And there was a pretty substantial effort, like one PR to do this that I built, I think was working on it over the course of maybe 2 or 3 months even, to basically turn chemistry featurization into mostly an interface with a couple of concrete things, and then kind of split out this other functionality into these other packages, so that if you just want to use chemistry featurization, you don't need to import this whole thing that has all of this PyCall and Conda and like a bunch of other packages that you're not actually going to use. And so you can take a look at the dependency list in the project file to see how much it really slimmed down, going from the previous version with all of this stuff to this much slimmer thing. And so, as I mentioned, you know, chemistry featurization today is mostly a lightweight interface that has a couple of concrete functionalities that we do export. It does support featurization of atoms-based systems, and we still maintain this separation of concerns between the kind of feature descriptors and this idea of codecs and featurization schemes. I only have a couple more slides. It's basically a little bit of conclusion and acknowledgement. I don't know, is that this slot is an hour, I guess, is that right? I have a couple of,
yeah.
Okay, right. So I have some stuff that I prepared to do a little demo of. I probably won't be able to get through all of it, but I have actually pushed everything that I was intending to do to the seminar demo branch of the chemistry featurization repo. So I'll zip through a couple of these things now to just kind of show you and give you a flavor. And if you want to see, there's of course the docs, which has its own kind of demonstration with a lot more commentary along the way. It's in a Pluto notebook. But this exact code that I'm running is also on that branch if you want to take a look. So hopefully, I think I'm sharing the whole screen. You guys see my VS Code now?
Yeah.
Great. Okay. So I've already imported all these packages here. I'll skip. So you can sort of manually specify graphs, and this all works. Maybe I'll just run this whole thing right now. So this is just, I just make a little adjacency matrix corresponding to just a triangle and say, okay, there's a carbon at every corner of that triangle. We have the little graph plot visualizer. But of course, that's not really what we're going to be doing most of the time. We're mostly would be interested in reading in actual structures, so we can read in a CIF file and visualize that. So we get something like this. This is actually a sort of layered structure. So you get actually a disconnected graph corresponding to the 2 layers that are in a single unit cell. But getting to the idea of how do we actually encode features. So if we want to encode the idea of which block of the periodic table we're in, so S, P, D, or F, we can construct this element feature descriptor that I mentioned to get the value of that feature on, for example, our triangle carbon. So this is, again, the value. This is not the encoding. That's carbon is a P block atom. Then we have this notion of the codec, which is the thing that takes care of the encoding of the value of the feature. And there's the function default codec, which if you don't really want to bother with kind of twiddling all of these dials yourself, the code will just sort of give you a default one, which in this case is this one hot. We call it one hot, one cold because it's both an encoder and a decoder. So we can see that if we can encode directly with that codec, and we get now this one hot vector style thing. So it's we can see the order in this case is DFPS because by default they're actually alphabetical. So you could force it to be SPDF if you wanted to. It of course doesn't really matter. And so the encoding there for a D is a 1 in that first slot. We have a decode function as well. So this is kind of crucial to that invertibility aspect. So we can, oops, that's a typo. I should probably fix that here. I'll commit that and push it later. So you can see that this decoding works fine. And you can, of course, also encode an entire structure, which will then sort of stack those vectors together appropriately. So the default behavior here, and I spent some time thinking about this, this is actually a little bit different from what some other packages do, but I just find this to be the most logically consistent. Whenever you're dealing with matrices, the first index is going to be the index of an atom. So 6 by 4, there are 6 atoms, and 4, the length of a feature vector is 4. Now, this wouldn't really matter if we were only ever talking about atom features, but what I found is as soon as we started doing pair features, where the sort of native format of the values, of course, this isn't the way that you would encode it for a model, ends up being these 3-dimensional matrices. It just gets really, really confusing if you do anything other than this very consistent indexing. So we can, of course, also do these continuous valued features. This works the way that I described with this sort of binning. So I won't run all this right now because I want to get to this other stuff. We can define custom features as well, where you provide your own lookup table. So here I just have a silly little meaning of life thing where carbon gets a 42 and arsenic isn't very friendly to life, so it gets a 0. And we can, as long as we're only encoding things that have carbon and arsenic in that, it will work. It will give us errors if that is not in fact the case. So we can build our element feature descriptor. It will work fine on our little triangle carbon. It just gives us a bunch of 42s. But if we try to encode this tungsten sulfide, notice this feature is not defined. So it will tell us that we can't encode some elements here. And we also have a function called encodable elements that we can call here, and it will tell us exactly which elements. And this also becomes really useful when you're building featurizations as just collections of feature descriptors. You can call encodable elements on that featurization, and it will give you just the intersection of all of the lists of encodable elements of the individual features. So you can check very quickly what things you can encode. So building a featurization, we have this, you can feed it the actual feature descriptors here. I recognize I'm going really fast. If you go through the demo on the Chemistry Featurization website, there's a lot more commentary that you can read that will hopefully kind of clarify all of this stuff. We can build a featurization, and there's a shortcut here to do it with just the names of the features. So if we use the function featurize, it returns this featurized atoms object. If we look at property names of that, that's just a container that has the atom graph, the featurization, and also the value of the encoded feature. So this gets at this point I was making about sort of carrying all of this stuff along so that we know exactly what we encoded and how we encoded it. We can decode as well. And what this gives us is just atom 1 has an electronegativity in the bin between 2.34 and 2.668. Its block is D, and its atomic mass is in this window. So again, when we decode those continuous features, we can't get an exact value, but we can get these bounds. And then finally, I made a little demo here, and maybe just so I can get to my last couple of slides within the time, I won't run this, but all that you need to do to make a featurization that can featurize an atom's base structure instead of a graph is this. So we define the featurization. I made a little sort of cheater constructor here where you can just build it from the graph node case. Of course, you could do something a little more elaborate here. And then the only interface function that we need to define it that isn't already there is the thing that tells us how to get the list of features. And then everything will just work. We can actually encode this. So maybe I'll just run this really fast so you can see that it runs. We load in the atoms. And then, oh, that's taking longer than I thought. Okay, well, at any rate, we can then encode it and it works. So we've implemented all that we need for this interface to work. So this was actually, I literally wrote this part all yesterday. I think you can see probably, yeah, the commit was 18 hours ago. I was really excited actually just how few lines of code I actually needed to make this thing work. There we go. So that will encode. So by default, again, it's returning the matrices corresponding to each feature individually, because we haven't, the other thing you can do with this interface is specify, how do you want me to combine these together? Do you want me to just concatenate these matrices or do something else? And if you don't tell it, then it's just going to return the encoded feature for each feature separately. So that's the matrix corresponding to block. We have 2 D block and 2 P block, or yeah, no, S, whatever it is. Anyway, so that's a very, very quick demo. I recognize I'm at the end of the hour here, so I'll just do the last couple of slides. So I promised some lessons learned. Julia interfaces are awesome. As Anant sort of aptly put it on Slack, I like how this PR essentially brings us full circle from wanting to be the interface package, realizing a type explosion is imminent, and becoming the interface package again. I thought that was a very sort of apt way to put it, and I didn't really have a better way to phrase it. I think another lesson learned is be willing to think big, but unashamed to start small. So what's actually concretely implemented right now here is nowhere near what is in something like DeepChem or any of these other big packages for sort of atomic machine learning. But I think the vision is big, and I think it has the potential to be a really wonderful and impactful thing. And hopefully, we'll keep working on it, and maybe we'll get some more contributors who can implement more stuff. And I think that the way that we're thinking about things is I hope the right way to do it. And I'd be really excited to collaborate with some of the folks over there. I think you guys are doing really cool stuff that's very, very related. And finally, just because this has happened to me so many times that I needed to sort of write this out, and I figured this crowd would appreciate this. Sometimes writing up the description of your problem to send to the Julia Slack is enough for you to figure it out. But when it's not, they'll probably still answer your question within a couple of minutes, even if you've been completely stumped for several hours. So very much recommend the Julia Slack as a way to get unstuck when you're debugging things. So my last slide here is just acknowledgements. So I want to thank, of course, ARPA-E and MolSI for the funding, and specifically my mentors at MolSI, Sina and Sam, were a really tremendous resource. Google Summer of Code for funding Anant, without whom a lot of this stuff wouldn't have been possible. Daria Gandhi, who's one of the lead developers of Flux, has been really, really helpful in kind of getting everything to play nice in terms of all the adjoints and things that we needed. Cormelian for helping me design the beautiful logo, and then my advisor here at CMU, Venkat. So that's all I've got. Sorry for going slightly over, but thank you all for the great questions and for your wonderful engagement.